Hello friends, my name is Dr. Sunil Kumar Jatak. Today I am going to discuss about the law of comminution. So this is the sixth lecture of non-ferrous metal extractions. So you are welcome in the channel Meta Engineering. So comminutions theory. Comminutions theory. What is the comminution theory? Comminution theory. Comminution theory is also called the laws of comminution. Comminutions. So this theory generally correlate the energy input and particle size particle size made from feed size. There are many theory are exist, but not theory is the satisfactory according to the Pills and Atkinsons. So the in the combinations, the energy is provided for reduction. From this energy, only less than 1% is used for the actual reduction. Most of the most of the part of this energy is utilized in heat production. Heat production. So this theory is another limitation of this theory is consider the particles. The consider the material is brittle in nature. So no energy will consume will consume in elongation or contraction. Elongation or contraction. So if the material will be the plastic, so the energy will be consumed in the changing the shape. So some portion will go this sides, and the it will retain the without creating the new surface. So only brittle materials is directly convert in the reductions, and it will not consume the energy in the elongation and contraction. So this is also the drawback of this theory. It does not give the idea in this case. So particles, this gave the particles come for the combinations for the size reductions is always in the brittle nature according to the combinations theory. So there are the many in the literature you found many empirical and semi-empirical relation, semi-empirical relation. These are called the laws of comminution. So widely expected laws are there have the three laws. First is the Rittinger's law. Second is the Kick's law. Third one is the Bond's law. So these are the three laws are used as the combination theory. So one by one we will discuss these laws. So first is the theory of von Rittinger's, which this theory is the produce. This theory is given by the von Rittingers in the 1861. This is also called the Rittinger's law, and in this, according this theory, the energy consumed in the size reduction is proportional to area of new surface produce. So the area of non-weight of the particles of the uniform diameter is inversely proportional to the diameter of a product size. So instead of this the equations of this theory is E is equal to P by M and K R d by dV minus T by dF. So E is the energy, P is the power, M is the rate of reduction in the tons per hour. dV is the product size, dF is the feed size. So there also have the some limitations of this theory is it does not give the idea about the mechanical losses. Mechanical losses means the energy is consumed in the fractions etc. So the energy consumption can be these losses can be predicted by running the cursor or grinding mills in running the cursors empty. So required energy can be calculated. So the overall energy efficiency energy required to create new surface, create divided by the total energy supplied. The theoretical effectiveness the theoretical effectiveness, the energy required to create new surface divided by the total energy supply minus energy for running empty. Running empty. So this is the this can calculate the actual energy consumptions, and this law is useful. This law is the applicable for the feed size less than 0.5 mm. So next law is the Kick's law. According to which the energy input is proportional proportional to the proportional to the size reduction ratio. We can write this form as so reduction ratio. First, what is the reduction ratio? Reduction ratio is the ratio of feed size divided by the product size. So Kick's law state can be write E is equal to P by M is equal to KK is the Kick's constants, and we can write this as df divided by dp. So here df is the feed size, dp is the product size, and p is the power, m is the rate, e is the energy which is consumed. So this law is the used for the coarse crushing, and second age so now this is the limitation. This is only used for the coarse crushing. Second is this law is the applicable. This law give that the energy required for reducing 200 mm particle to the 50 mm size will be same as that for reducing a 2 mm particles to 0.5 5 mm. So these are the some limitations of this law. Third law is the Bond's law. This law is given in the 1952 by the Bonds. So Bond's law is the immediate and more realistic. It is an inter intermediate and more realistic method of consumption and grinding. Second is the state age of this law is the required work required to form particle size from a varying large particles is proportional to the square root of the surface, square root of the surface to volume ratio of product. So we can write that E is equal to P divided by M is equal to K. K is the Bond's law. We can write the Bond's law, and the under root of SP divided by BP according to this law. So here we can write the SP divided by VP is equal to 6 by dP particle size. So we can rewrite this formula E is equal to P by M is equal to kV, and here can we write that root 6 by dV, and can we write kV is equal to 1 by root dV, 1 by root dV. So feed size is very large, and 1 by dP can be the negligible. 1 by dP is can be the negligible because the feed size is the very high. So kV is depends on the type of the machine used and materials to be the crushed on. So the more precisely we can write the Bond's law is equal to P by M is equal to kV, and 1 by dP minus 1 by dP dF. Here can be rewrite. Here is the 2 points that should be the remembers. So like the diameters in the micron, diameter in the micron, which 80% of product passes passes is designated as pin, and 80% feed passes consider as F. Work input is in the kilowatt, can be right, and so here W is equal to 10 Wi divided by P minus 10 Wi divided by root F. So the Wi is the work input, work index. Wi is the work index. In the form of work index, we can write this law as E is equal to P by M 0.3162 Wi 1 by root dp minus 1 by df. So Wi is equal to kV root 0.1, because we can say feed the df is approx infinite, and dp is 0.1 mm. dp is the 1 mm. dp is the 1 mm. So by using this we can write this, and you can find the k. We can put at the place of the kV this, and the work index can be write E is equal to P by M is equal to Wi. So from here we can write this, and work index as the gross energy kilowatt hours per tons of the feed required to reduce the very large feeds to such that 80% of the product will pass through the 100 micrometer, or can say 0.1 mm screen. So 1 mm screen. So here we can write the product size will become the 0.001, and this portion is become as the negligible. This portion become the negligible as compared to the feed product, because feed size is the very high and dp is the very small. So this is the negligible, and so this is the k, and 0.1 is the put here. So and at the place of this we can write the wi. So wi is equal to kv by under root 0.1. The work index of the materials may be the difference to materials to materials. So work we can write material and work index. For the limestone, It is 12.74, and 4 gypsum rock. Gypsum rocks, it is the 6.73, and quartz, it will be 13.57. Coal, for the coal, it is the 13. For the bauxite, it is 8.78. So bulk index may be the different for the different material. Hope this video will be the beneficial for you, and you will like this video. And you have any doubt, you can write in the comment box. Thank you. And for the more information, you can study the mineral processing books. Mineral processing books, I have written the books here, these books. Thank you.